so quietly, that would be better, because we want to stay on time. So today it's a great pleasure to have two great speakers for the tutorial on automatic machine learning. The first speaker is Frank Katter, who is a professor at the University of Freiburg. And the second speaker is Joachim van Schoren, assistant professor at Eindhoven University of Technology and founder of OpenML.org. Together, they organized the AutoML ICML workshop for the past 5 years, and they're actually organizing the meta-learning workshop later this week on Saturday. Frank will start, and there's going to be, depending on time, maybe a 5-minute break, during which you can also ask questions. There are 2 microphones, one on each side of the central aisle. Please line up behind them, and we will call you. All right? And without further ado, Frank.
Yeah, thank you very much for the introduction. While people are trickling in, let me make one point. So we have slides available for this tutorial. If you go to your browser and you type automl.org, and your browser works, then you can get the slides there. Now that there's a lot of people, the internet is maybe not so strong anymore. So this worked 10 minutes ago. Likely it's not going to work for you either then, but the slides are available. They're online. Interesting. We don't have that on the screen, but all you would see is a browser that's trying to load. Oh, and it did load now. No. Well, never mind. AutoML.org, that's where the slides are. And if you go to AutoML tutorial, so do AutoML tutorial here on automl.org, that's where the slides are. And all the references in both my slide set and the one of Joachim are actually clickable links, so you can just directly use the slides in order to explore the literature. All right, with that said, let's start the tutorial. So this tutorial is on AutoML, which is the quest for using machine learning and optimization in order to make machine learning better, in order to make machine learning more robust and easier to use for people without expert knowledge in machine learning. So to briefly give some motivation, we live in very exciting times, of course, for deep learning. We've seen tremendous progress in speech recognition and computer vision for self-driving cars, in reasoning and games, and deep reinforcement learning, etc. But all these advances are based on expert knowledge of some very brilliant people who have gathered a lot of expertise in deep learning and know how to set all the hyperparameters. So if you want to apply deep learning to a new problem domain, that is, of course, it's a problem that deep learning is very sensitive to a lot of different hyperparameters, such as architectural choices and choices in the optimization pipeline and the way you regularize your network in order to generalize to new unseen data. And so it's you easily get between 20 to 50 design decisions that you need to make in order to start to train your network. And that leads to the current state of deep learning practice. Given a new data set, you need an expert that chooses the architecture and the hyperparameters that would work well for this data set. And then, given that architecture and hyperparameters, you can apply deep learning in an end-to-end fashion to learn features from the raw data. But unfortunately, even experts don't always know exactly how to choose the architecture and the hyperparameters for a new data set. So you end up with this iterative loop with a human in the loop, the human expert, having to choose architectures and different hyperparameters, exploring that space in order to, at the end, actually get a nice deep learning system that gets state-of-the-art performance. What AutoML tries to do is to provide this kind of one-stop shop. You put in the data, and then there is this big box here that does end-to-end learning, that does learn features from raw data, but also already decides about which architectures to use, which hyperparameters to use, etc. One way to achieve this is, of course, to mimic this manual approach up here, where you have well, some deep neural network. So you can have some learning box that could be just a deep learning framework. And you have the expert choosing architecture and hyperparameters here. You replace that by a meta-level learning and optimization process that reasons about which architectures work well, which hyperparameters work well on this particular data set, and that can also reason across data sets. One note, this learning box here, this is not constrained to be a deep neural network. It can also be some traditional machine learning pipeline where you need to clean and pre-process your data, select and engineer better features, select a model family and its hyperparameters, and construct ensembles of these models. And you can also do meta-learning, meta-reasoning about which types of hyperparameters work well in these frameworks. So the outline of the tutorial is as follows. We'll first talk about modern approaches to hyperparameter optimization, which might sound as a somewhat boring topic, but if you don't get automated hyperparameter optimization inside of your inner loop, then, well, you can't really do AutoML. So it's really important to have a robust and efficient core of your machine learning pipeline. Then we'll talk about neural architecture search, and then about meta-learning. I'll cover the first two of these, and Joaquin is going to talk about meta-learning. All of these are based on a book that we edited. In particular, these are the 3 first chapters of that book, basically review articles about these 3 different fields. So the outline for my part is, well, first I'll talk about hyperparameter optimization, phrasing AutoML as a hyperparameter optimization problem, then black box optimization methods for hyperparameter optimization, and then going beyond black box optimization in order to gain efficiency. For neural architecture search, the overview will basically mimic that. First, there is search-based design. How do you write this as a optimization problem? And then again, black box optimization and speed-up techniques. The first part is based on this review article that I wrote together with my brilliant PhD student, Matthias Feurer, who deserves a lot of credit for this. So let's get straight in. AutoML as hyperparameter optimization. Let's define the hyperparameter optimization problem we're talking about first. So we have some algorithm, some machine learning algorithm A, and it has hyperparameters lambda with domain capital lambda, and so we'll use lambda throughout the tutorial for hyperparameters. And you have a loss that depends on your algorithm with hyperparameters trained on a training set and validated on a validation set. And the HPO problem is just to find the hyperparameter setting that minimizes this loss, the validation loss. All right. What are these hyperparameters? Well, there's continuous hyperparameters, of course, such as learning rates. There's integer hyperparameters, such as number of units. There's also categorical hyperparameters that are maybe a bit more interesting than continuous and integer ones. These categorical parameters are discrete, so we can't differentiate through them. They're finite domain and unordered. So some examples here might be, well, you might just choose between different algorithms, machine learning algorithms, support vector machines or random forests or neural networks. Or you might choose activation functions in your neural net, such as ReLU, leaky ReLUs, or TANHs or so. And you might also choose operators that operate on your latent feature representation, such as convolutions, separable convolutions, max pooling, et cetera. And these categorical parameters will come in very handy later on when we do neural architecture search and want to write neural architecture search as a hyperparameter optimization problem with a fairly generic version of what constitutes a hyperparameter. And a special case, of course, of categoricals is binaries. Another type of hyperparameter is a conditional hyperparameter. And so conditional hyperparameters B are only active if some other hyperparameters A are set in a certain way. And these conditional hyperparameters allow us to write pretty generic search spaces as a hyperparameter optimization problem. So one example is Adam's second momentum parameter. If you don't use Adam, then this hyperparameter is not going to be active. It's not even going to be inspected, and it's provably unimportant. If you don't pick Adam, then you don't need to pick the second momentum parameter. Likewise, if you have a parameter that's a convolutional kernel size of a certain layer, if the type of that layer is not convolution, then this hyperparameter is not going to be active. And as a final example, well, if you have a support vector machine's kernel, you only need to choose that if you actually use a support vector machine. If you use a random forest instead, then provably that SVM's kernel parameter is not going to be inspected. So with that notion, we can actually write AutoML as a hyperparameter optimization problem as follows. So there's this combined algorithm selection and hyperparameter optimization problem where you have several algorithms, A1 to AN, and each of these have hyperparameter spaces. And you again have a loss function, and now the problem is to find the combination of the best algorithm and its hyperparameters to jointly minimize this loss. And with that, you can actually write this combined algorithm selection and hyperparameter optimization problem as just a hyperparameter optimization problem, where you have one top-level hyperparameter that's a choice of machine learning algorithm, and all the other hyperparameters are conditional on that choice. You don't have to stop at one level of conditionality. Actually, kind of the first AutoML system that we worked on, AutoWeka, had 4 levels of conditionality and a total of 768 hyperparameters. So a pretty big space that wouldn't typically be called hyperparameter optimization, but the same type of algorithms actually do apply to that as applied to a low-dimensional continuous space. So I am referring to all of this as hyperparameter optimization just for simplicity. All right, so I hope to have convinced you that hyperparameter optimization with a general notion of what constitutes a hyperparameter is a pretty powerful beast. So let's talk about some black box optimization methods for doing hyperparameter optimization. So if you have, for example, a deep neural network and you have different hyperparameter settings here, you have a black box that trains this deep neural network and validates it. You get out validation performance. Well, what black box optimization does is treat this as a black box and seek for the input, lambda, that maximizes the validation accuracy. So you just search for the lambda that maximizes f of lambda. And with that, you throw away all information about what happens inside of that black box. And well, you give up a lot by doing that, but it gives you a generic interface for applying this to all kinds of different problems. This black box function is, of course, expensive to evaluate, so sample efficiency is important. We can't evaluate this too often. The arguably simplest approach for doing hyperparameter optimization is grid search. This is, of course, exponential in the number of hyperparameters. It's useful for if you have 1 or 2 hyperparameters, but if you have a lot of hyperparameters, it's probably not the best method. Random search, in contrast, is only exponential in the number of important hyperparameters. So if you have, for example, 1 unimportant hyperparameter here, and you have 1 important parameter, then what random search does with this budget of 9 function evaluations here, you get 9 different values for this important parameter, and therefore can use your budget much more effectively than grid search, which would only get 3 values for this important parameter and get each of these evaluations 3 times because the unimportant parameter doesn't matter. So random search definitely does perform better than grid search if you have some unimportant parameters, and oftentimes you have parameters that are not completely unimportant, but you definitely have some hyperparameters that are far more important than others, such as learning rates. And so random search is a useful baseline because of that, but it does have the problem that it doesn't follow the information. It doesn't actually learn anything about the space. If in one part of the space performance is dramatically better than in other parts of the space, random search will just not care about that at all. And that is suboptimal, and one approach that does care about this is Bayesian optimization, which is a very popular approach for black box function optimization. It works as follows. So you fit a probabilistic model to the function evaluations that you have made. So let's say we have evaluated the function here and here. So we have 1 hyperparameter here. It's just a single hyperparameter because I can't make a nice figure in n dimensions, but it directly translates to that case. And here you have the true function here in dashed. And we have evaluated it here and here. And what Bayesian optimization does is to fit a probabilistic model to these function evaluations in order to predict for unseen hyperparameter settings what the performance would be like. Typically, you use Gaussian processes for this, which give you a mean function here in a solid line and an uncertainty estimate here in this blue funnel. And you use this uncertainty estimate in order to trade off exploration versus exploitation. So exploitation in areas where the function is predicted to be high, in this case we're maximizing, and exploration in parts of the space where you haven't evaluated yet. This trade-off is formalized by means of a so-called acquisition function, and there's various different acquisition functions. One popular one is the expected improvement over the best point seen so far, and this is plotted here. What you then do is to optimize this acquisition function over your hyperparameter space to find the maximizer. Then you evaluate your function at that point, refit your model to, in particular, get lower uncertainty estimates around here and also a somewhat different fit globally. Then you recompute your acquisition function, optimize your acquisition function again, and evaluate the next point, and you iterate until you're out of time. Now, this is a very popular approach. It's been around for over 40 years, and it's very sample efficient. It also works when the objective is non-convex, noisy, has unknown derivatives, so all the types of characteristics that we do actually face in hyperparameter optimization. And there's also recent convergence results depending on some assumptions on the smoothness of your response surface, etc. One example for Bayesian optimization, I got an email today from Nando de Freitas, who knew that I'm giving this tutorial, and he told me finally he can tell the world that Bayesian optimization was actually very crucial inside of AlphaGo. So here's some quotes of his email, which are quotes from a forthcoming paper of his with Yuchan Chen. So I'm just going to read this to you. So during the development of AlphaGo, its many hyperparameters were tuned with Bayesian optimization multiple times. This automatic tuning process resulted in substantial improvements in playing strength. For example, prior to the match with Lies et al., we tuned the latest AlphaGo agent, and this improved its win rate from 50% to 66.5% in self-play games. This tuned version was deployed in the final match. Of course, since we tuned AlphaGo many times during its development cycle, the compounded contribution was even higher than this percentage. So I think this goes to show nicely that in practice, Bayesian optimization definitely can have impact. And I would have been very surprised if Bayesian optimization was not used in AlphaGo, knowing that Nando is at DeepMind and was involved in the project. Good. So Bayesian optimization is a very powerful method. However, there's some problems for the standard Gaussian process approach for this general AutoML framework, where we have a lot of hyperparameters, a highly conditional space, this mixed, discrete, continuous hyperparameters. You have high dimensionality with low effective dimensionality. And for each of these problems, there are fixes, but they're kind of just non-standard fixes. The noise is also sometimes heteroscedastic, so different hyperparameter settings yield different noise. For example, it might also not be Gaussian. It might be multimodal, for example, if some runs diverge and some runs converge with different learning rate settings. And Gaussian processes are not necessarily the most robust method in terms of their internal hyperprior. You need to set hyperpriors in order to get the best performance, and you need to pick the right kernel for your application at hand. There is actually some work on picking the right kernel automatically, and this goes towards pushing Gaussian processes towards more robustness. So I'm looking forward to that being applied in a lot of different packages. Also, the model overhead is not necessarily, can be a problem because Gaussian processes scale cubically in the number of data points. So if the black box function is truly expensive, then typically this doesn't matter too much. But in multi-fidelity approaches, then you can actually get quite a lot of function evaluations, and then this model overhead can actually matter a lot, and you need to resort to approximate Gaussian processes. A different model that has also been used sometimes, in particular in my own work, is a random forest model, which is kind of a simple approach that works out of the box. It's not very sensitive to its hyperparameters. It can directly choose the important features. It can directly work in high dimensions with mixed continuous discrete hyperparameters, etc. The only thing that's not so nice about it is that it's not a great probabilistic model. It doesn't have this nice probabilistic interpretation. And we do need uncertainty estimates for Bayesian optimization. And what we use here is typically frequentist uncertainty estimates. So we just model the variance across the individual trees' predictions. So if all the trees predict the same thing, then we're certain. If the trees predict something different, we're uncertain. So it's a simple model that we actually use in the 700-dimensional space. There's also work on Bayesian optimization with neural networks. In particular, there's two different types of works. One just fits a standard neural network and then takes the last layer and does a Bayesian linear regression of the learned features in that last layer. It's called DINGO, Deep Networks for Global Optimization. And the follow-up work that we did is using fully Bayesian neural networks that are trained with stochastic gradient, HMC, and well, just give a full Bayesian interpretation. And these networks can give you very nice predictions. So for the regime of the data where there's lots of data, it gives you very good predictions with very low uncertainties. And in the areas of the space where there's not a lot of data, it gives you large uncertainties. So that's precisely what you need in order to do Bayesian optimization. However, so far, to the best of my knowledge, this actually hasn't been studied for high-dimensional spaces, for conditional hyperparameter spaces, discrete spaces, etc. So that is actually definitely an important area to follow up on. A final model for Bayesian optimization I want to talk about is this tree of Parson estimators. That's actually quite different. It does not model this probability of the function given the hyperparameter, but instead it models a density estimate of the probability that a hyperparameter setting is good and the probability that a hyperparameter setting is bad. So I'm making an example here. So let's say we have evaluated this function 4 times. We want to minimize now. There's 2 bad points up here and 2 good points here. And so you fit these density estimators. And then you look at the probability of being good divided by the probability of being bad and use that as an acquisition function. This acquisition function has been proven to actually be equivalent to expected improvement by Bergstra et al., which is why people view this as a Bayesian optimization algorithm. So then you optimize this acquisition function, get this new point, refit this kernel density estimator for bad points, recompute your acquisition function, maximize that, then evaluate here. And by evaluating here, now you have another good point. And this point here was previously good, and now you have other good points, so this becomes bad. There's a hyperparameter saying which quantile of points you call good and which quantile of points after which you call it bad. And so the pros of this method are that it is very efficient. These kernel density estimators can be fit very quickly. It's very parallelizable and very robust. It kind of just works for all kinds of different dimensionalities, etc. One con is that typically it is actually less sample efficient than Gaussian processes when you have the right kernel for the Gaussian process. A final model that is not Bayesian optimization that I wanted to mention is population-based methods, because they're also used in neural architecture search. There you have a population of different configurations, and you want to maintain diversity, and you don't want to stagnate. You don't want all the configurations to be the same. But you also want your population to improve over time. One example of population-based methods are evolutionary strategies, and they work as follows. So you have one incumbent point. You sample, for example, from a normal distribution around that point, evaluate all these different points, then pick the best ones, and move your incumbent over to be a weighted average of your good points. A popular variant of evolutionary strategies is CMAES, which is a covariance matrix adaptation evolutionary strategy, which basically wins this black box optimization challenge every year. That is about cheap function evaluations. So if you have a budget of something like 1 million function evaluations, then these evolutionary strategies are a lot better than Bayesian optimization. Bayesian optimization is really just not targeted towards that and would also be far too slow in that setting. And well, recently we also looked at how would CMAES actually do for hyperparameter optimization, and it showed that it is actually quite competitive. If you have parallel resources, then it can actually be better than all the Bayesian optimization methods that we tried. It, however, only works on purely continuous spaces. All right, so that was an overview of different black box optimization methods. Now I'll talk about how to speed things up. Why do we need to speed things up? Because this black box view is just really too slow for deep learning and for big data sets. If doing a single function evaluation takes a week or so, then well, getting 50 samples would take a year, and obviously we don't have a year in order to do our hyperparameter optimization. So there's 4 different types of approaches for going beyond black box optimization. Meta learning I will not talk about, because that is part 3 of this tutorial, and Joaquin will talk about that later. And there's a lot of different approaches here. I will briefly talk about these first 2, and then focus on multi-fidelity optimization, because that is kind of the most mature method right now and is at a stage where you can use it as a tool. So hyperparameter gradient descent is the first one I want to talk about. This formulates the hyperparameter optimization as a bi-level program, where you have this outer objective where you want to minimize the validation loss of, well, as a function of your hyperparameters, lambda, and your internal model parameters, w. The w's are set by optimizing an inner loss, namely the training loss, given a hyperparameter setting lambda. So for example, you optimize with SGD to get W star, and then you want to get this validation loss. And you can also phrase this as getting gradients with respect to the validation loss by, for example, deriving through the entire optimization process that leads to this W star. This sounds expensive to start with, and it is indeed expensive in terms of memory or time, so you can choose. But if you have a lot of hyperparameters, then this can actually be very useful, because you don't just get a single function evaluation out, but you get a whole gradient out. However, this approach is somewhat expensive, and another approach is actually to interleave optimization steps with respect to the validation performance. You do a gradient step of the hyperparameters, and then you do a gradient step with respect to the parameters of the training loss. This, interestingly enough, works actually quite well in practice, but there's no theory about why this works and where this might fail and so on. So this is actually a very interesting area of research that I would encourage people to work on. And just in general, if you can do gradient-based optimization, then of course there's a lot of cool things that we can do. And neural architecture search is actually also going this direction with using a lot of gradient-based neural architecture search. I'll talk about that in a bit. The second way of going beyond black box optimization is to do probabilistic extrapolations of your learning curves in order to do early stopping. So you have an initial learning curve, and you want to know, well, where does this go? Will this do well, or will this not do well? And so you can learn to extrapolate. For example, you can use parametric learning curve models that are fit with MCMC to do these predictions, or you can also use Bayesian neural networks in order to do these extrapolations. The final way of going beyond the black box function is to do multi-fidelity optimization. So what is multi-fidelity optimization? It's about using cheap approximations of the black box function. In cheap approximations, the performance on which correlates with the actual black box function. So you want a cheap approximation where if a hyperparameter setting does well there, typically it also does well on the expensive black box. How can you get these cheap approximations? Well, in a variety of different ways. For example, you could look at subsets of your data. You could look at fewer epochs of SGD. In Bayesian deep learning, you could do shorter MCMC chains. You could do fewer trials in deep reinforcement learning. And we've actually done all these four. You could also do downsampled images in object recognition. We haven't done that, but I'm pretty sure that that also would work. And this approach also is actually applicable in a lot of different domains, such as fluid simulations, for example. You could use less particles in a fluid simulation or do shorter simulations. So it's really a generic optimization trick that applies beyond hyperparameter optimization. So how do you use these multi-fidelities? Here's an example. This is an SVM fit on MNIST. This is the entire MNIST data set, 50,000 data points. And here there's roughly 400 data points. And the two most important hyperparameters, C and gamma. And you see that the response surfaces actually look quite similar. In particular, you don't want to do a lot of function evaluations over here in order to figure out that this area of the space is bad, if you can figure this out already on these much cheaper approximations. And importantly, doing function evaluations over here is about 10,000 times cheaper than over here because SVMs scale superlinearly in the number of data points. So you want to do many cheap evaluations on the small subsets and few expensive evaluations on the large data set. And if you do that, you can actually get up to 1,000-fold speedups over doing Bayesian optimization on the expensive black box function. How do you do that? Well, you fit a Gaussian process model that takes as input the hyperparameters and the budget, and then predicts how well that will work, and then chooses both lambda and the budget in order to maximize the bang for the buck. So for example, you maximize information gain per time spent, information gain about where the global optimizer lies. And there's a variety of different methods that all fall into this general sense of multi-fidelity Bayesian optimization. However, this is not trivial. There's quite a few approximations involved. It's kind of hard to code up. And also, well, you need to get the right kernel. If you have high dimensional and conditional spaces, this might not actually be the best approach. And a much simpler approach would be to, for example, just sample a bunch of random configurations on the cheapest setting, on the cheapest fidelity, take the best fraction thereof, move them to the next budget, take the best fraction thereof, move them to the next budget, take the best fraction and move it to the next budget. This is the approach called successive halving. And here's another visualization of successive halving for a different fidelity, namely wall clock time. So you evaluate a bunch of hyperparameter settings, all for this initial wall clock time. You take the top performing ones, continue them to the next fidelity, take the top performing ones, continue them, take the top performing ones, continue them. And voila, you get something that you would do as a human. You wouldn't continue this poor learning curve here all the way for a week in order to see that it didn't work. But you would cut it off early. There could be one problem, however. If this learning curve here actually does continue going up and give you the best performance, then successive halving would never find it, even with an infinite amount of compute power. And this is a problem that the extension of so-called hyperband fixes. So hyperband actually calls successive halving iteratively, one time in the most aggressive way, with starting from the lowest fidelity. Then, my computer is freezing. This is not good. Interesting. Oh, great. Uh-oh. OK, the presentation just died for no apparent reason. I will restart it. Sorry about that. So where were we? We're talking about hyperband. So hyperband first calls successive halving on this most aggressive bracket, then calls it again, starting from this less aggressive setting, then calls it again, starting only from here, and then calls it again, only using the full black box. So given an infinite compute budget, you would actually find issues where, so you would find the best configuration, even if this is the best configuration and continues up here. I think I'll stop using the laser pointer because then my presentation does not want to continue. Hyperband has a lot of advantages. You have strong anytime performance due to these multi-fidelities. It's general purpose for low-dimensional and high-dimensional spaces, conditionalities, and so on. It's all not a problem. It's very easy to implement. It's also scalable and easily parallelizable. However, it is based on random search. And so it doesn't exploit knowledge about which hyperparameter settings work well. And that's where Bayesian optimization is strong. So therefore, we combined them to get the best of both worlds. We used Bayesian optimization in order to pick these configurations, and then used Hyperband in order to allocate their budgets. Just to visualize how this works, so Hyperband versus random search. Initially, Hyperband is much faster. Given enough time, it's actually not much faster than random search. Bayesian optimization is the reverse. Initially, there's no speed up over random search because you need to explore the space first in order to figure out where the good points lie. But given enough time, you actually converge faster to the optimum. You can speed this up by doing meta-learning, and Joaquin will talk about that. But if you don't have meta-learning, if you learn from scratch, then, well, it's not going to be better than random search to start with. But using multi-fidelities, you can actually make it better than random search in the beginning and also in the end. So this Bob approach has almost linear speedups by parallelization. So that is also not a problem. And that is why for practitioners right now, if you ask which tool should I use, I would recommend, if you have multiple fidelities, I would recommend Bob because it does combine the advantages of TPE and Hyperband. It's kind of this tool that if you don't want to think about it, it would work quite well. Other multi-fidelity Bayesian optimization methods might also work well if you fit the kernel correctly. If you don't have access to multiple fidelities, I would still recommend, if you have low-dimensional continuous spaces, standard Bayesian optimization with Gaussian processes, for example, Spearmint. If you have high-dimensional categorical conditional spaces, I'd recommend Bayesian optimization with random forest, as in SMAC, or this TPE method based on kernel density estimates. And if you're purely continuous and you have a relatively large budget and maybe want to parallelize really nicely, then CMAES can actually be very competitive. There is several open source tools that are based on hyperparameter optimization. So AutoReca I already mentioned. This is based on the Weka machine learning framework in Java and SMAC as an optimizer. There's HyperOptSKLearn, which is based on scikit-learn and TPE. There's AutoSKLearn, also based on scikit-learn and SMAC, or in a newer version on Bob. This also uses meta-learning in order to jumpstart the optimization and post-hoc assembling. And it won the AutoML competitions, well, the first one and the second one. There is a third one going on right now, and there's going to be a workshop about challenges in machine learning where that's going to be discussed. There is TPOT, which is also based on scikit-learn and evolutionary algorithms, and it focuses more on pipeline construction. And finally, there's H2O AutoML, which is based mostly on random search, but also stacking and very efficient implementations. I would like to mention that AutoML can be viewed as a democratization of machine learning. AutoSKLearn actually didn't only win against other AutoML systems, it also won against human experts in a Kaggle-like competition. In particular, it performed better than up to 130 different teams. And it's really easy to use. It's BSD licensed, and it's a plugin estimator for scikit-learn. And it already has a lot of community adoption. So this really opens the door kind of for everyone to use effective machine learning that can, in some cases, actually work better than human experts. If the human experts don't have domain knowledge kind of beats everything. If you can generate better features, then that is, of course, very helpful. One quick example application of AutoSQLearn. So in a collaboration with Freiburg's robotics group, they were interested in this binary classification task. A robot had an object in its hand and wanted to place it down and was wondering, will the object fall over or not? We used a data set of 30,000 data points for which a bachelor student actually manually created 50 features. And then, back in the day, this was 2015, he used Caffe and spent about 3 months to get to an error rate of 2%, which was a very nice bachelor thesis. Everybody was very happy. And after that, AutoSQLearn got completed. And, well, we actually got to a 0.6% error rate in 30 minutes. This is not to diss the bachelor student. He actually generated these features without which AutoSQLearn wouldn't have done anything. But it goes to show that deep learning, if you don't have expertise, if you haven't played with this a lot before, is not necessarily the best tool for a given application. So you should also look at simple baselines, in particular if you have featurized data. Again, not to diss deep learning, all the rest will be deep learning. Because deep learning is, of course, awesome and can generate abstract representations of the data from raw features. So the second part will be on neural architecture search. This is based on this review article I wrote with my PhD student, Thomas Elsken, and a research scientist at Bosch, Jan-Henrik Madsen. And this is also chapter 3 of the AutoML book. So let's first talk about the search space design. The simplest search space design is a chain-structured space. So you just have to decide how many layers do I want, and for each layer, what is the type of this layer? Is this going to be a convolutional layer, a max pooling, a fully connected, etc.? That was historically the first type of space people looked at, but then over time, people looked more at more complex spaces with multiple branches and skip connections, inspired by ResNets, etc. Since last year, the types of search spaces pretty much everyone is using is now actually a cell search space in which you parameterize a building block that takes some input and yields some output. And then you stack these building blocks together, very much like residual networks or inception networks. Typically, people have 2 different cells, one regular cell and one reduction cell that reduces the spatial resolution of the image. And typically, this macro architecture here is just a chain structure. You could also think of doing a multi-branch or skip connections in this macro architecture. Nobody really does that, but the multi-branch and the skip connections are in this individual cells that you stack. These cell search spaces have 2 advantages. The first one is that you can, well, they're actually very small compared to a general space where you parameterize this entire network here. And therefore, you can search them more efficiently. And the second advantage is that if you have found a cell on a small data set, such as CIFAR, then you can actually use that cell on a larger data set, such as ImageNet. And this actually does give you better performance and has improved the state of the art for ImageNet and other large data sets. One disadvantage of using the cell search space is that, well, you're constrained to, well, you will not find entirely new architectures. You will only find cells that you will stack in this macro architecture because the macro architecture is defined manually. So if you want to find completely new architectures, then one might want to go beyond the cell search space again. So I promised that I'll talk about how you can phrase neural architecture search as hyperparameter optimization. So here's a cell search space that Sof et al. Used. Basically, they had this recurrent neural network controller, which would pick first, the first hidden state that goes into your cell, then the second hidden state that goes into your cell. Then it would pick the operator to use on your first hidden state, then the operator for your second hidden state, and then a combination operator. How do you combine the results of your 2 branches? That could be just an addition or concatenation. And So you end up with 5 categorical choices for each of these blocks. The first categorical choices has domain 0 to n minus 1 if you're in the nth block, because those are the hidden states you could pick. These categorical choices here have just different operations such as max pooling, separable convolutions, etc. And this last categorical choice has very few options. So you have 5 categorical choices for each of these blocks, and you have B blocks, with B typically being set to 5. And with 5, this gives you 25 hyperparameters that fully define the cell. And there isn't even any conditionality going on here. This is just categorical hyperparameters. And standard hyperparameter optimization methods can be used in this space. If you have an unrestricted search space, then you can still write that as a hyperparameter optimization problem, but then you have conditionalities. And you can only, you have to have a limitation of the maximum number of layers. So for example, if you just have a chain structured space, but you're not going to restrict this, then, as a hyperparameter optimization problem, you still need to say, a maximum number of layers, such as 10,000 or so. And each of the layers that is not active, so you have this top level hyperparameter that's number of layers, and everything that's larger than that, all the hyperparameters are just not active. All right, so that's how you can write neural architecture search as hyperparameter optimization. Let's next talk about some black box optimization methods for neural architecture search. The method that really popularized neural architecture search in the community was this neural architecture search with reinforcement learning by Beresov and Kwok Lee. What they used is a recurrent neural network controller to sample the architecture, individual blocks at a time. And then they trained the child network with that architecture to get some accuracy, and used reinforce in order to train the parameters of the controller. This became really popular because they were the first to achieve state-of-the-art results on CIFAR-10 and also on a language dataset, PenTreeBank. However, they used very large computational resources, 800 GPUs for 3 to 4 weeks, 12,800 architectures evaluated, etc. That is why recent work really looks at going beyond the black box function. But if you have these large computational resources, then this was the first paper that could actually really achieve new state-of-the-art performance with an automated pipeline. There's lots of other work on black box optimization. For example, neuroevolution algorithms actually go back to the 1990s. Typically, what they did is to optimize both the architecture and the weights with evolutionary methods. And that doesn't scale to very large networks, as well as stochastic gradient descent, which is why more recent methods based on evolution actually only use evolution in order to get you an architecture and then train it again with stochastic gradient descent. And here you can see nicely that initially you could just start with some very simple architecture, and then you evolve this over time to become more and more complex and better performing. And these evolutionary strategies, not evolutionary strategies, evolutionary algorithms are actually the best known approach on this one data set, CIFAR-10. They were actually compared in a head-to-head comparison by Kwok Lee's group, and evolution actually did better than reinforcement learning. And this evolution approach really just uses this fixed length search space. There's no neural networks going on in the controller. There's just a simple evolutionary algorithm picking these 50 different hyperparameters. So 50 because it's 2 cells, each with 25 hyperparameters. Another approach that has also been used for neural architecture search before it became mainstream is Bayesian optimization. So back in 2013, James Bergstra actually did this joint optimization of a computer vision pipeline with 238 hyperparameters using TPE. And in 2016, we had AutoNet that actually was also part of the AutoML challenge and was the first AutoDL system to win a competition dataset against human experts. Bayesian optimization with Gaussian processes is a bit harder to use for neural architecture search because you need the right kernel. And There are some kernels for neural architecture search. Already in 2013, there was this ARC kernel. And in 2018, there's this NASBot kernel. A somewhat related method to Bayesian optimization is sequential model-based optimization, which also uses a surrogate model in order to pick the architecture to evaluate next, and also yielded state-of-the-art results compared to reinforcement learning recently. All right, so that was Bayesian black box optimization for neural architecture search. We already saw most of black box optimization for hyperparameter optimization anyways. And now we look at going beyond the black box. There's 4 different approaches again. I will not talk about these last 2. Meta-learning, well, I'll say 2 sentences. That there's actually only 1 paper. It's here at NIPS. That basically learned a controller across different data sets, and then given a new data set, has already a controller that's warm started and can find good architectures for this new data set faster than when learned from scratch. There's 2 papers using multi-fidelity optimization with Bob. Yeah, one just doing standard joint architecture search and hyperparameter optimization, and one doing the same in a reinforcement learning context, where you optimize the policy network and the parameters of the reinforcement learning algorithm, etc. All these 3 papers here don't do neural architecture search in this really big space, but actually have only a couple of different options for the convolutional neural networks, but also some hyperparameters that are optimized. I will talk about these 2 approaches, weight inheritance and network morphism, and weight sharing and one-shot models, because those actually we didn't see in hyperparameter optimization. These are special to neural architecture search. The first one is based on, well, network morphisms. Network morphisms are operators in neural architecture space that change the network structure, but not the modeled function. So for example, if you have a network and you add 1 layer that you initialize with an identity mapping, then you have a new architecture, but you have the same function. And this allows for efficient moves in architecture space. So you have some architecture with a given performance. You apply some network morphisms to, for example, add a layer, or sorry, extend a layer, add a layer, or add a skip connection. Then you train for a little bit, just a few epochs, to optimize these new weights, typically improve performance. And then you pick the resulting model that's the best and iterate. It's a very simple approach that actually yields a very efficient architecture search. You can do architecture search in about a day on a GPU using this. The second approach I want to talk about is weight sharing and one-shot models. So in 2016, there was a paper on convolutional neural fabrics that basically embed an exponentially large number of architectures in this so-called fabric here. This is a fabric, and each path in this fabric is 1 neural network. So the idea is kind of similar to Dropout. You train, well, actually, not here yet. So you train this neural fabric. You train all of the different paths at the same time, and basically you get an exponential ensemble of different architectures. But there wasn't any, the relationship to Dropout wasn't that clear here yet. That became more clear in this paper, Simplifying One-Shot Architecture Search, which actually used path dropout in this, well, one-shot model. They called this neural fabric the one-shot model. And they used path dropout to make sure that the individual models don't really rely on the other models, that you don't just do well as an ensemble, but also that individual models do well. There is another related approach that uses reinforcement learning, also using this one-shot model, and that samples 1 path at a time in that one-shot model, trains its weights, and therefore also trains all the weights of all the other models that share some part of the path. And there is one other approach that's somewhat different for weight sharing. This one trains a hypernetwork that generates the weights of different architectures. So the architecture is an input to the network, and the network outputs the parameters to use for this particular network. And what's shared is, well, there's only one hypernetwork that's being used to generate the weights for all the different architectures. So this can also be understood in this weight sharing view. One of the currently most popular approaches for neural architecture search is DARTS. It stands for Differentiable Neural Architecture Search. This relaxes a discrete math problem to look at the one-shot model, but for each of the operators, you have a weight alpha that you use to multiply the result of this operator. So you have this cell architecture, and you don't know from here to here which operator should you use. You could use 3 different ones, and you initialize them uniformly, giving them all the same weight, and just add the result here. And then you actually, in the space, you do gradient-based optimization using a very similar approach as I mentioned before in hyperparameter optimization by Locatina et al. To interleave optimization steps with respect to validation error of the architecture parameters and with respect to training error of the weights. And then you end up with some architectural parameters that are much stronger than the others. And in the end, you just take an argmax and take the most promising architecture. And this is basically because you have these interleaved optimization steps of validation, one step, gradient step with respect to validation error, one gradient step with respect to training error. You're only maybe a factor of 2, 3 slower than a normal optimization of your training error. And therefore, you can now do a neural architecture search very efficiently. There's a lot of questions here, like why does this work if you just interleave these steps that are currently being studied. There's a lot of different promising works under review. For time reasons, I'll just give you a very brief overview. So there's several ICLR submissions that are actually following up on DARTS. There's also interesting follow-up work on hypernetworks. And there's also an interesting line of work on multi-objective optimization and neural architecture search to very explicitly give you neural networks that work well with resource constraints, for example. I do want to leave you with a couple of remarks on experimentation in neural architecture search. So the final result of different methods is often quite incomparable due to a variety of different reasons, namely different training pipelines are being used. There's no source code available often. There's different hyperparameter choices, and there's different search spaces and initial models. And that all makes it very hard to compare different methods. It's nice when people release the final architectures, but it doesn't help for comparing the different algorithms to each other. For the different hyperparameter choices, there's actually very different hyperparameters during the training and then during the final evaluation. And it's quite important where these hyperparameters come from. If you have to do hyperparameter optimization of your method in order to then do well, then it doesn't work really well as an AutoML system because that should just work off the shelf given a new data set and you shouldn't have to optimize it first. And well, it also matters whether you start from random or whether you already start from a state-of-the-art neural network and only improve that locally. So if you review neural architecture search papers, I would ask you to maybe look beyond just the error numbers on CIFAR, but look at the method itself and ask for these details. Also, we just need benchmarks that are not just CIFAR, but that are maybe CIFAR with this search space, with this training pipeline, with these hyperparameters. And then we can compare these different neural architecture search methods on a fair basis. Finally, experiments are often very expensive, and so there's also a need for cheap benchmarks that actually give us some information about which methods work well, so we can do a lot of runs and get statistical significance. All right, to wrap up, hyperparameter optimization and neural architecture search are really exciting fields. There's several ways to go beyond black box optimization, and one shameless advertisement. So we're building an AutoML automatic deep learning team. We want to actually build a research library of different building blocks for efficient neural architecture search. We want to build an open source framework, AutoPyTorch, and we have several openings on all kinds of levels. With that, I'm at the end of my part, and we'll now take a 5-minute break. I encourage you to stretch your legs, maybe go to the washroom if you need to, but we'll also take some questions during this period. All right. Is that questions? There's mics. I don't really see, so if you're at a mic, just tap on it and ask away. And Joaquin, maybe you could come set up.
I have a question.
Right.
For searching on these continuous hyperparameters, it always seems like there's an extra question of the range and maybe the scale of the hyperparameter, and how do you handle that sort of thing?
Very good question. So if you have a very large range, then it's going to be very hard to find the optimum. So it's going to be less efficient. If you have a small range, then, well, you might actually not include the optimum for this particular data set. So this definitely is an issue. What you can do with TPE is you can actually specify a prior over what you expect to be a good hyperparameter setting. So the priors work much nicer in TPE than they work in standard Bayesian optimization, because a prior in Bayesian optimization would be, well, I expect the function value to be this given this hyperparameter. In TPE, the prior is, well, I expect the learning rate to typically be good around 10 to the minus 3 or 10 to the minus 2. That's a prior that's much easier for humans to give. And then you can just specify a Gaussian centered where you think it should be centered, but also giving the search an opportunity to overwhelm that prior if there is enough data suggesting otherwise. Thank you.
In the recent advance of neural active research, we've seen methods which uses reinforcement learning or genetic algorithms, while for hyperparameter optimization, we tend to see more Bayesian optimizations. Do you see any reason for this change, or is this a matter of taste of the different authors?
I think the reason clearly is that Bayesian optimization works really nicely for low-dimensional continuous spaces with Gaussian processes. And most of the Bayesian optimization community really comes from Gaussian processes. So that's where that's the type of problems that they deal with all the time, where Gaussian processes do well, and that's where Bayesian optimization methods are being developed. With new kernels, they also do apply to neural architecture search, et cetera. And we are starting to see some approaches. And well, we've used random forests, et cetera, in these high-dimensional spaces before, but we're kind of an outlier in the Bayesian optimization research community with that. Most other people use Gaussian processes. I think also with Bayesian neural networks, they're extremely promising, and that could really appeal to another whole different community, namely the Bayesian deep learning crowd. So when they start using Bayesian optimization with Bayesian neural networks, I think we'll also see a lot more of that type of work for neural architecture search. The flip side, why haven't we seen a lot of reinforcement learning for hyperparameter optimization? That's a good question. That might also actually work quite well. And we do see evolutionary algorithms for hyperparameter optimization, just kind of not at NIPS, because these papers tend to be rejected at NIPS. They appear at Gecko and other more evolutionary algorithms communities.
Thank you. Great talk.
Same microphone, yeah.
Hi. So I just was curious if you had any thoughts on, I guess I'd call it auto ML. So
Yes.
Learning a neural network that knows how to optimize the hyperparameters of other neural networks generically. Obviously, this is slower, but it has the theoretical advantage that you run this exactly once for everything on the outer loop, and then you only run the normal two-stage optimization. Is there any work in this area?
Yeah, so this is a very good question. In fact, there will be an auto DL competition where you have to submit a system that just does everything. And the system kind of optimally would be the result of this process that generates this auto DL framework. And what you want to do is, of course, well, use a lot of different data sets, reason across data sets. So we'll see a lot more about that in the meta-learning part. I think, well, that's really where you can get this inductive bias from what are these spaces typically like and what performs well in these spaces. And yeah, there's not much work on that yet, but it's definitely very exciting. And I think we will see quite a bit of work in that realm.
Okay, cool. Thank you.
Thank you. Other mic? Okay. Joaquin, if you want to set up.
Okay. Perhaps it's a little bit naive question, but do you have a high expectation that these search methods will lead to finding any very interesting and novel architectures? Like, for instance, with NAS, okay, well, it did work a little bit better on ImageNet, but it wasn't a massive improvement, and it doesn't really seem we learned anything about building better architectures as compared to, let's say, building ResNet, where we did learn something.
This is a good question, and I think I'll really leave it for time to tell. I think now that we have more efficient neural architecture search methods, where actually a lot of people can use them without having access to Google scale computational infrastructure, I think we'll see thousands of people starting to use these methods and maybe come up with something cooler and really understand more about the space. We're not there yet, but I would expect that we will get there in the next couple of years.
Thank you.
Do you want to set up? And then maybe one final question.
Can I? No.
Sorry. How do you compare reinforcement learning approach and the Bayesian method in terms of the sample efficiency, parallelization, computation efficiency, all different kind of problems?
So I would generally say Bayesian optimization tends to be more sample efficient, but there haven't been any head-to-head comparisons. So actually, we're working on one. After that, I have some data for that, but my expectation would be that it's going to be more efficient in terms of Bayesian optimization. Bayesian optimization tends to work well, particularly for these low-dimensional spaces, where reinforcement learning is not geared towards that as much.
Thank you.
Right, thank you. And I think if we can move over. All right, thank you. And there'll be another question period later.
Yeah, sorry, we have to cut the questions a bit short because we are running short on time. Next up is going to be Joaquin.
Thank you. Hold on. It's a bit busy here. So good afternoon. My name is Joaquin van Schoren, and I will talk about learning how to learn. So Frank has told us a lot about what you can do when you're giving a new task and you have to start from scratch. But typically, as humans, we never run into the situation. We always have some kind of prior experience that we can use to solve the task more efficiently than when we would have to start from scratch. So I'll talk about that. So learning is a never-ending process. Imagine that you are a small baby. The first time, if you learn to walk, it's very, very hard. You fall down a lot. You have to do many, many tries before you can pull it off. But next time, when you learn to ride a bike or do something else with motor skills, this becomes a lot easier because you have first learned how to walk, right? Babies don't start riding bicycles. They first start learning how to walk. And every time we encounter a new task, we learn how to do it more efficiently based on prior experience. And that process, that arc, we call meta-learning. We learn more efficiently with less trial and error and less data. So what's actually happening here is that we transfer an inductive bias from prior learning iterations to the new task, right? So inductive bias is any assumptions or priors that you put into your learning system except for the training data. And if we can extract useful information, like constraints or beliefs or representations from previous tasks, the new task becomes much easier. And we'll see a range of different techniques that do exactly that. The underlying part is that the prior tasks have to be similar. You can't just transfer information or assumptions from tasks that are very different. They have to be somehow similar. If not, then you may actually harm the learning, right? Okay, so we call this field also meta-learning because we collect metadata about prior learning episodes, and then we transfer that to the meta-learner. So the meta-learner gets a bunch of metadata and has to make sense of that and use it in a useful way to then construct a base learner that then will do the actual modeling. Now sometimes this is somehow squashed together and the meta-learner will directly build models, but we'll come back to that. So I'm subdividing this field into 3 levels, each one requiring more and more similar tasks. So the first type of problems is where the tasks can be very different from each other. And then we just generalize general knowledge about tasks, right? It's typically what humans do when you're confronted with a task which you're not familiar with. You just try whatever worked well in the past in general, not very specific, just something that always works. That's the thing you try first. Right? Then later on, when we have more information about the task, and so I can compare my task to prior tasks, then I can reason about, okay, how is this task different from my new task? And then I can actually transfer information in a much more useful way. And then finally, we come to tasks which are so similar that I can actually take a trained model from a prior task and then repurpose it for solving my new task. So the first type of tasks, this is where the task can be quite different. So there we look at the performances of previous approaches. And we also look at exactly what we did. And we encode that as a configuration. That's the whole set of assumptions, like the neural architecture, the algorithm, the pipeline of steps you built, hyperparameters that you tuned, all these things that uniquely define your model, that's your configuration. This is the lambda here. Okay? So giving a configuration and a task, I get the performance out of it. And then my meta-learner has to take this configuration and the performance and I figure out how to use that usefully to solve a new task. So the first and simplest way to do this is simply remember what worked well in the past. Then you build a general ranking of which are the best approaches. And then when you encounter a new task, you just go top to bottom. You try the method that works well in general, always the best, then the second one and the third one. Right? Very general. And this is also useful as a warm starting technique. So if you're considering, for instance, Bayesian optimization, you can start with the overall top 10 configurations to warm start that approach. Another thing you can do is you can configure your design. Right? If you're a meta-learner and you're facing a problem with many variables, the first thing you want to do is kind of eliminate the variables that make the problem harder. Right? That's what we do here. So here we, for instance, look at which hyperparameters are really important to tune and which one can I just leave at default. One way of doing this is called functional ANOVA. That's work by Jan van Rijn and Frank Hutter. So here you take every hyperparameter individually, you vary it, you see what the effect is on the performance, and if you see that a hyperparameter has a large effect on performance, you say, this is the one I want to keep. If not, you throw it out of your search space. Okay? Now, you can say, sometimes you have hyperparameters that have a lot of variance, but they also have a very good default. And if I just keep it at default, I'll be fine. That's defined in tunability. So here you first learn a good default, and then you measure how much improvement can I still get if I tune that parameter. Right? And then I rank my hyperparameters based on the tunability, and I use only the top ones. And the final thing you can do is you can look at which tasks did I solve that were similar, and what did not work, because I will not try that again. Right? It's like it's a learning experience. You try something before, it failed horribly, you don't want to try that again. Right? Okay, now you can look at how similar tasks are in hindsight. So here you have a new problem, you try a couple of approaches, and then you see how these different approaches worked. And then you can start reasoning, okay, if this worked and this didn't work, which other tasks do I know from the past where this was the same. So if two tasks have the same performances for similar configurations, then that means that those tasks must be somehow similar to each other. Right? And one way of expressing this is with these relative landmarks. You just remember the performance differences between two configurations. And if two tasks have correlating relative landmarks, then that means that those tasks are likely similar. Right? Are you going to use that? So the way you use that is you're first going to start with a good configuration, you evaluate it, and then you say, okay, which tasks are now similar based on this outcome? Then on the similar tasks, you look which other configurations do I know that were better than my current one, and then I use the best one of those. And I start again, I get one new evaluation point. I again update my similarity of my data sets. I choose another competitor based on what worked well on the similar tasks. And that gives, and I repeat this way until I stop doing that. This is a fairly effective way of solving this space if you have no other information to work with. Now we've seen Bayesian optimization, so you'll also build a lot on that. So basically here you learn solving a single task. You try a number of configurations. You have performances, you'll build this regression model, and then you can use that to choose a new configuration. But unfortunately, when you do this and your task is done and you're giving a new task, you kind of forget all this useful information. Right? And you don't want that. What if we can actually learn the surrogate models, learn very well what worked on a specific task, and then transfer that to new tasks so I don't have to start from scratch again? So one way of doing this is surrogate model transfer. So here we say that a task is similar if, well, you assume that if the task is similar, then a surrogate I learned on a similar task will again be useful. I can start from there. Right? So there's basically two ways of doing this. First of all, you build a surrogate model, or you remember your surrogate model, you store it per task. So for every task, you have the surrogate model that you learned. And then when you have a new task, you're going to combine all these surrogate models from all these tasks. And there's two ways of doing this. One is to first measure a distance between tasks, and then you basically weight the contribution of each surrogate model based on how similar the tasks are. If you have a very similar task, then you give more weight to the surrogate model. If it's a very dissimilar task, you're going to ignore it. Another nicer way, I think, is to build a new Gaussian process, a mixture, that's weighted by the current performance. So first of all, you build a mixture. You let all of these GPs make a prediction. And then you see, OK, on the new task, how well were they doing? And if some of them were doing very well, you increase their weight. If some of them were doing very badly, you decrease their weight. It's like having a bunch of advisors. If some of them give you good advice, you listen more to them. If not, you listen less to them. Now, this one thing here, always with the GPs, there's always this question of scalability. And of course, if I give you millions of data points from previous tasks, it's a pity you cannot use them in one large surrogate model. And this was kind of solved by people at Amazon, Valerio Perrone and his colleagues. So they said, OK, I can't train a Gaussian process, but I can train a linear Bayesian optimizer, which is linear in time. Okay. Now, of course, this linear surrogate here is probably not a good approximation for my hyperparameter that I'm trying to model. Right? So, but what if I can add the second degree polynomial, the third degree polynomial? Then I can represent the behavior of this hyperparameter much better. So then the question is, OK, if you do that, then which polynomials should you use? Because some hyperparameters are very linear, some are very nonlinear. So you have to learn from each hyperparameter how you should model that. And in this case, we learn this with a neural network. So we give the neural network all the configurations, all the performances, and the neural network has to learn what's the optimal basis expansion, what's the optimal set of dimensions to build this model in. If you do that, then you can simply fit a linear Bayesian regression model in there, and you can use that perfectly well for making predictions. That scales much better. Another thing you can do, you can combine the Bayesian, well, your surrogate models from different tasks using multitask Bayesian optimization. So the way this works is like in the figure here. So assume you have 3 tasks, the green, the red, and the blue. At some point, you want to predict for the blue task, but you have a lot of uncertainty. Now, if you can include information from the red and the green task, you get more information about this high parameter, for instance. So you get a much better estimate of performance. So you actually use information from other tasks for this specific task, the blue one. This is very nice. It's not so scalable. This was solved not so long ago by Frank's group using Bayesian neural networks. So these are neural networks that output a mean and an uncertainty. And the nice thing is you can also use these in a multitask way. And then you can exactly do this in a multitask way and be efficient as well. A final thing that's been done by people at Google, Vizier. It's an algorithm where you assume that the tasks that you get in are sequential, and every task you have is sort of similar to the previous one. What you then do is you look at your previous task, you see where you were wrong. In this graph, you can see sometimes you were underestimating, sometimes you were overestimating. And you're going to transfer that to a new task because you're going to start with a prior that's equal to these residuals. It goes to these residuals, right? So if you were previously overestimating this point, now you start with a prior that starts underestimating it. And that way you correct for that, and then you can transfer useful information from previous tasks to the new tasks. It's also very cool. Okay, this was all without any information about the tasks. What if I can now look at my task and tell how it's similar or dissimilar to other tasks? Now to do that, I need some way to characterize my tasks. And we call these meta features. These are measurable properties of the task that we can use. These are simple things like the number of instances and features, but we'll come back to that. So we give our meta learner basically our performances, our configurations, and the meta features of the tasks. And then it can use those meta features to measure how similar two tasks are. And that's very useful information, of course. If you have a good estimate of how similar a previous task is, you can meaningfully transfer more information from that task to the new task. So one way of doing this, well, you have these meta features. One way is using these handcrafted meta features that have been in the literature for a while. These are simple things like the number of instances, because more instances make easier learning. The number of features, because more features make it typically harder. The number of missing values and outliers also make learning harder. Statistical things, just as skewness and kurtosis, but also correlation. Is my feature, do I have many features that are correlated with my targets? That's good. Do I have features that are correlated in between? That's not so good. So you want to collect that kind of information. There's also things like information theoretic things like class entropy or the mutual information between a feature and a task tells you about how much information there is in the task. Things like model-based features where you build a simple decision tree and you see how complex the tree is. That tells you something about how complex the task is. And things like landmarkers where you simply run a number of simple algorithms and you use the performance as kind of a landmark of how difficult this task is for that type of algorithm. Besides those, you can also learn representation. That's typically useful for things like images and sound. So here, one way of doing this is using deep metric learning. And a common way of doing this is using Siamese networks. So here you take two data sets, two image data sets, can be MNIST and CIFAR, whatever. You put them through first a feature extractor, can be convolutional nets. Then you give them to meta feature extractor. Then you push them through some layers, and it at the end gives you a vector for each data set. Now, if data sets are similar, those vectors are supposed to be similar, right? So then you are going to use an external ground truth measure, for instance, using meta features. That gives you an error signal. And then you can say, okay, if the two vectors are very dissimilar, but the tasks are actually very similar, you backpropagate that error to the network, and that way you learn a representation. So after the training, This will allow you to put in a new data set, you get a vector back, and you can use a vector as a way to measure distances between this task and any other task of that type. Now, if you know how similar two tasks are, one thing you want to do is to use things that worked well before. Right? One way of doing this is with genetic optimization. So here you want to start your genetic process, your evolution, using pipelines or configurations that worked well before. So you look at the meta features. You use something like the L1 norm to measure which tasks are similar. You use the pipelines or the configurations that worked well on those similar tasks, and you start with those. You start with those pipelines that worked well on similar problems. You can also do this for Bayesian optimization. So here you initialize your Bayesian optimization using a number of configurations that worked well on similar tasks. Frank already explained that this gives you a significant boost in performance. And it's something that's always generally useful, right? You learn which tasks are similar, you transfer information from those similar tasks to a new task. Another nice approach by Nicola Fussi here at Microsoft is using collaborative filtering. So here you consider that the configurations are rated by the tasks, just as users rate movies. Here, the task rated configuration. Right? If configuration is good for the task, it will get a high rating. Kind of the similarity here. So now you use matrix factorization as you would do before. So you start out with this matrix P. You fill it with all the evaluations that you have. This will be a very sparse matrix. Then you use matrix factorization to learn a latent representation for your tasks and your configurations. And that means that now every configuration, every pipeline, every neural architecture you have is one point in this latent space. Right? So now you compressed the information from a very large dimensional space to a very small dimensional space. In that small dimensional space, you can easily fit a Bayesian optimizer. You can do Bayesian optimization. And you can then use that to find better pipelines in your space. Right? And of course, you need probabilistic matrix factorization because you need the uncertainty here. But otherwise, that's it. It's a very cool technique as well. OK, then you can also directly learn a mapping between the meta features and what you want to use. For instance, you can do similar things as before. Like instead of warm starting by looking at a similar task, you can build a meta learner that takes the meta features and then gives you a ranking of well-performing configurations. Right? So this is basically replacing the KNN type of approach of ITSK-Learn with a meta model that uses random forest or XGBoost or something. You can learn more complex patterns. You can also use this to look at your meta features and then say, OK, now for this data set, you need to tune these high parameters, or you can configure your search space this way, or you can even train meta learners that take the meta features and a configuration and then predict the performance. Right? On this task, this method will perform this well. This is sort of like a surrogate model, but more general, you can use any model for this. You can now integrate these meta models in other HTML pipelines. What's often very useful, for instance, is to train a meta learner that predicts how long an algorithm will take to run. Because that way, if you have a choice between two algorithms, and they're equally performant, estimated, but one is much faster, then you probably want to start with those configurations, those algorithms that are faster. Right? That helps you make predictions, to search the space more efficiently. OK, now, we seldom learn a complete algorithm from scratch. We often decompose the problem into several parts, and then we solve those parts individually. And one way that we do this is using these pipelines. Right? We don't write an algorithm from scratch. We first pre-process the data using existing algorithms, that we learn from the data using existing algorithms. And this pipeline structure is something we all use, and it helps to significantly reduce our search space. Right? So, OK, But if you want to explore a space that's defined by the pipeline, can you do that efficiently? And well, if you can do this, then it's easier to learn because the individual parts are easier to learn. You can transfer information from one pipeline to another pipeline, and it's also more robust. Right? So one way of constraining this space is to discretize this space and only try a number of fixed pipelines. And this is what's, for instance, done in this work by Nicola Fussi, where they beforehand discretize the space, and this apparently works quite well sometimes. You can also impose a fixed structure on the pipeline. This is what AutoScaLearn does. They start with a number of preprocessing steps, then a number of things like PCA and feature selection, and then they build a classifier. And this, again, constrains the space of what only these pipelines you can build. Right? Another thing you can do is hierarchical task planning, where you break down the task into subtasks and again subtasks. So for instance, in the beginning, you choose whether you're going to classify this using a pipeline or end-to-end with a neural net. And depending on the choice, you have other choices. And that, again, helps you to break down the search. And here, you can use meta-learning, again, to make decisions. You can use warm starting to start with pipelines that worked well before. Or if you have to make a decision between including or not including a component or going left or right in the search tree, you can use meta models that advise you what you should do. And you can, again, search the space more efficiently. One particular way is using pipelines. So there, of course, you're not going to start with very complex pipelines. You start with very simple pipelines, and you evolve them as much as needed. Right? So the complexity is defined by the complexity of the problem. And again, you can then evolve them. The mechanisms, you can take a pipeline, and then you can mutate it. So you can change a component, okay, remove it, or you can add one, or you can tune the hyperparameters. Or you can do crossover, where you take two pipelines, and then you cross them over. You get two new pipelines, and then you hope that these do better than the ones you had before. Okay. This, again, allows you a more efficient space. And also, if you discovered something like a pipeline that does a crucial step in your process, this part of the pipeline gets populated more and more often, so this information gets spread and more useful. So different approaches for doing this. The most well-known is TPOT. So this builds tree-based pipelines. Basically, you start with a data set, you take multiple copies, you build simple pipelines, like you do PCA or you do polynomials. And at some point, those pipelines can come together in a feature join. So you take these features and these features, and this becomes your new pipeline. And so these pipelines are like tree-shaped, and this allows you to build very complex pipelines very efficiently. Another method is Gamma. It's very new. This is more or less the same, but in an asynchronous way. So you're not stuck waiting for stragglers in your generation. This does evolution asynchronously. And Recipe does a grammar-based approach. And again, you can use meta-learning. Although it's not really done yet so much, you can use it efficiently, for instance, for warm starting the search or for using meta models that help you choose between options. Another interesting approach is building pipelines through self-play. So here again, you build pipelines by inserting, deleting, and so on. But you start off with a number of trees that are randomly generated. You evaluate them, and then you train a neural net to predict how well a configuration is going to work. Then this neural network also predicts some actions you want to take, like adding a component or removing a component. And you send that information to Monte Carlo tree search, which then does a number of simulations. So it builds a number of pipelines, goes to the network, asks, is this going to work well or not? Yes, then I pass it on, or I do more of these kind of simulations. And at the end, it uses the feedback from the neural network to generate good pipelines. And the neural network gets the evaluated pipelines, learns more about which pipelines work well, and this way, the algorithm basically does self-play with itself. So there's no input here. There's nothing comes from before. It just does self-play and explores by itself. Okay, then finally, we want to learn from trained models. So here, the tasks have to be very similar. Right? You cannot transfer from very different tasks. So here your meta learner gets performances, it gets configurations, exactly how did you build this neural net, for instance, and it gets the model parameters of the trained models. And then it has to use those to learn more efficiently. The easiest way that we all know is transfer learning. So here you have a source task and a target task, and you need a way to find which source tasks are similar. But if you do, you can transfer models from the source task to the new task. And typically this works by either using that model as a starting point, and then you tweak it later on, or you freeze certain parts, like you freeze the architecture, but you update the weights. And there's different ways of doing this. There's been a lot of work here, for instance, in Bayesian networks, where you start with a trained Bayesian net on a similar task, and you do minor changes until you find a new Bayesian net that works well for your task. Or reinforcement learning, you can go from one task to a similar task by taking a policy and only changing it a little bit. Now, something we've all been doing probably in our universities these days is transfer learning with neural networks, because there it works very well. This is, for instance, the thing we all do in Keras, for instance. We take a neural network, convolutional neural net, we build layers, and then if you look at the filters at each block here in this convolutional net, you can see that first it learns simple things like these lines and colors. Then you get more complex things like dots, and later on you detect eyes and shapes and so on, right? So you can use this as the part that learns useful features, and then you can learn other tasks just by adding to it. And so here it's very important to see how similar the tasks are. If they're very similar, then you can, well, and if it's small, you can typically just freeze the network and then add some layers at the end, and you just train the new layers. If the dataset is large and similar, you just add layers at the end, and you retrain end to end. And if it's large but different, you want to unfreeze part of the network and retrain it again. But you need more data from there. But even with all these approaches, this will fail if your tasks are not similar enough. And this is something we don't really understand right now. We don't know when a task is similar enough for transfer learning or not. We typically just try it, and we adapt when it doesn't work. So there's a lot of work in real learning to learn new algorithms through data. So one critical example is the one from Joshua and Bangio, who actually, well, they consider the brains probably don't do backprop, so we're going to replace it with a simple parametric update rule that was inspired from neurology. So you have this update rule where you have the learning rate, some presynaptic activity, then a reinforcement signal, and you parameterize this, and then you learn basically what the optimal settings are for this update rule, and then you can search for different update rules this way. Later on, Runnison and Johnson, they replaced it with a neural net. So here the weights of your neural net become your hyperparameters, and then you kind of optimize those. So after optimization, you end up with a new update rule that you can use. And then afterwards, this was replaced again by an LSTM. Right? So you use your LSTM to learn a good update rule for training neural nets. That proved out to be not so scalable, and then nothing happened for, well, not so much happened in the meantime. But then Marcin Andrićević and colleagues at DeepMind, they replaced this LSTM with a coordinate-wise LSTM, which is much more scalable, much more flexible. So that's the green block here. And then so this is your meta learner, your meta model, it's your optimizer. And this has to learn the update rule for a model, the optimize Z. I have a new word. So at some point, this LSTM gets an error signal from the optimize Z, from the model, and has its current state, and then uses that to make a prediction about how the weight should be updated. That's this GT here. So here the axis is time again. So the original weights come in, then you add the weight update to it, you get new weights, you get again an error signal, the LSTM gives you a new update, and you move all the way to the right, At some point, there is evaluation, you get a loss function, you back propagate through time the error, and that way this LSTM gets trained. This means that this LSTM is now able to learn a new update rule that's specifically good for the type of tasks it's trying to solve. Right? And you can then remove this Optimus Z, replace it with another Optimus Z, or use a new task, and you can train this optimizer to be very good at doing the weight updates for a range of similar tasks. Also nice that this is now one single network, like the brain. It's quite cool. Of course, if you want to transfer information from previous tasks, it will be cool if you can now also use this to learn from very little data. Okay? Because neural nets typically take a lot of data to train. What can we do to train from very few examples? And this is an image from Hugo La Rochelle, who's actually giving a talk in the meta learning workshop about future learning. I think this will be very, I'll encourage you all to go there. So the problem here is you're giving one task, and this one task simply consists of 5 classes. You get one example of each class, and then you have to make predictions. So you have to predict which class this is, which class this is. But you don't get just one example of these tasks, you get a lot of these examples. And your meta model now has to learn a set of ways, well, you need to parameterize your model, and then you need to learn the parameters so this model can solve this task efficiently. Okay? And then basically you look at the loss of this model, and then you look at what is this loss over a number of tasks, and that's your error signal that's your cost for the meta model. And the meta model uses that to then find better parameters, and then that way learns how to build a model for these tasks. There's a whole range of techniques to solve this problem, and different ways of building meta models. So one thing you can do, you can start with an existing algorithm as a meta learner. You can, for instance, start with an LSTM, and you do gradient descent. I'll talk more about this soon. Another very popular approach is MAML, where you just learn the initialization of your network, and then you do gradient descent. And then there's a whole bunch of techniques I can't go into, but they all have some kind of memory component. So they remember instances from previous tasks, and they use them in the new tasks. And these are either KNN-like techniques, or you learn embedding in a classifier, or you also have these black box models. There's typically some neural network that has memory components that can use the memory from previous tasks and apply the new tasks. And these are actually state-of-the-art right now. Yeah, so one thing you can do is very general. It's not the most performant algorithm, but it's very generally useful and very elegant. Is, again, you use an LSTM for this. So if you LSTM meta learner here, and you're going to make this observation that if you look at the gradient update rule, right, your weights are equal the previous weights minus learning rate times the gradient. And if you look at what the LSTM cell update does, so your LSTM state, your memory, equals your previous state times the forgetting gate times the hidden state times the input gate. So if you now say, okay, let's just equal this theta to this CT, and this green one to this green one, and this one to this one, then I can train my LSTM, and if I've trained that, then I also have my update rule. Right? I think that's very cool. So then you can solve this problem by starting with any random initialization. You train your model on the first task. You get an error back. Then the LSTM uses its current hidden state to generate a new set of weights. You train a model, you get an error back, and you keep doing this until you end up in your test set. Then you can evaluate the cost of this LSTM. Then you can backpropagate this through time. You update all the settings of these LSTMs. You have a new theta 0. You go back and forth, back and forth, back and forth. And so you train your LSTM to be very good at updating the weights of these base models. And you also learn a good initialization at the same time. Another approach that's very popular is this model agnostic meta learning. So here you don't bother with building complex LSTMs, you're going to learn new skills quickly by just starting from a very well initialized neural net. Right? The goal is here to train a neural net on a bunch of similar tasks so that it has a very good initialization, and whenever it needs to solve a similar task, it can start from that initialization and get optimal models much faster. So if you look here, you have the current initialization, theta. Then you look at, in this case, 3 tasks. For each of these 3 tasks, you take k examples, you evaluate the gradients, then you update the weights for each of these subtasks. And then you update this gradient theta to minimize the sum of these per task classes. And that brings you to a new initialization, which is hopefully closer to the optimal weights theta 1 to 3 here. It's a very cool algorithm. So you learn the initialization for a number of tasks, and whenever you have to solve a similar task, you can just start from that optimized initialization. This has been shown to be very resilient to overfitting. It also generalized better than the LSTM approaches, and there's even a proof of universality where they can prove that there are no theoretical downsides to doing this. So if you just learn a good initialization and use gradient descent, this will never be worse than learning a very complex neural net to learn an update rule. Okay. And more recently, Reptile was released. That's a more scalable version of this that uses stochastic gradient descent. So instead of actually doing this thing every step, it does k steps for one task and only then updates the weights. So it's a bit more scalable. Okay, then also another useful tool for meta-learning is reinforcement learning. Right? This comes very natural. You can just have a reinforcement learner that has to create a new algorithm or a new model, and then we can just evaluate the model and use the performance as a reward for the reinforcement learner. And then the reinforcement learner has to learn over time how to build an optimal model. And the main goal here is to actually solve reinforcement learning problems much faster than before, because humans are typically very good at playing new games faster than reinforcement learning algorithms are. So the idea here is that you build a meta reinforcement learning algorithm that's typically a deep RNN, and you train it on a large number of environments, and this algorithm then has to implement an agent that then for a similar environment has to learn a policy. You look at the performance, you give the performance back, then that way it can learn a policy over many environments. And so this way this reinforcement learning agent learns how to create a new reinforcement learning agent that's much faster at solving similar tasks. Okay? And it actually also works for future learning. It's a more recent paper by Juan. So here you do future learning by not conditioning only on the observation, but also on the upcoming demonstration. Right? So here you have a bunch of demonstrations per task. So you train this meta learner to build a reinforcement learning agent, not knowing what the actual demonstration is going to be, but it will be maximally prepared for solving tasks that are similar to the ones it's been trained on. Right? So it learns how to build RL agents for similar tasks. And in this whole range of other tasks that you can solve with meta-learning, one thing is active learning. So here you can build a deep network that learns representation of your data, and then a policy network. And so whenever it receives a state and reward, it just tells you which other points you query next. Then you use meta-learning to train the network and the policy network. You can also do density estimation by just learning a distribution over a small set of images, and then you use MAML, MAML-based future learner to learn densities much faster than otherwise possible. Or you can also do matrix factorization this way. The bottom line here is that you can take basically any algorithm, like active learning, density estimation, matrix factorization, and you can replace existing algorithms by a new algorithm that you learned. Right? This is very powerful. You can replace these handcrafted algorithms by learned ones. Okay, that's the end. So finally, maybe you're wondering, yeah, I want to do meta-learning, but how do I get useful metadata to work with, to train my models? Well, we've been working on this platform called OpenML. So you can go there, it's openml.org. It has thousands of uniform data sets. You can download them all en masse, and they're the same formatting, so you can run your experiments on all data sets simultaneously. Each data set gets 100 of these meta features, so you can measure distances between tasks. You get millions of evaluated runs, and these are all evaluated with the same splits, with different metrics. And for a large bunch of them, you also get the traces. So whenever a model is optimized, you get all the sub-models that were optimized running up to that, and the models that were built, for some of them, not for a lot of them. And then you have APIs in Python or in Java. So here you see the Python API, for instance. So it's a very simple interface. You download the task with an ID. Then you build whatever classifier you want. In this case, it's just a scikit-learn classifier. You transform that to a flow. A flow is our representation of a pipeline or a learning object. Then you run the flow on the task. Then you get a run, which you can store locally, or you can also publish it. So these 5 lines allow you to download lots of data sets, run lots of models, and also share those models again with anybody. And it's always run locally. You download data, you run algorithms locally, and you share the results globally. And this allows you to do never-ending learning. You can build an algorithm that works against this API, downloads data sets, learns how to learn over many tasks, shares its results, its model, with the server, and then other agents, other bots can then download this model again and use them. So this gives you a platform where you can exchange information about meta-learning. And you can also easily build if you want to experiment with meta-learning, this is the best way to start. So you can easily write your own bots to learn well over a large number of tasks. And we also have benchmarks. So here you can see, for instance, a visualization. So every dot here is a model. This is performance, higher, better. This is time. And you can see all these color dots are dots built by humans. And these orange dots are dots built by robots. And these robots, they can just learn by themselves, or they can actually look at the models from previous robots or previous humans, and then use that to do meta-learning and build new models faster. And by the way, we have some openings for a programmer and a teaching PhD, if you're interested in building this very cool platform. Okay, on a final note, I think we have made a lot of progress in the last years. I think we're made a lot of progress into making a real human-like learn-to-learn happen. I think this is a crucial aspect of science because this gives humans a significant advantage. If you can solve one task very well, that's fine. But if you can learn how to solve any task, that's much more powerful. Right? And it's something we should definitely put more effort into. It's also a universal aspect of life, not just of humans. Trees learn, the universe, well, life in general learns all the time. So it's time we understand this process. It's a very exciting field. There's many unexplored possibilities, and many aspects are completely not understood. For instance, task similarity. When can I transfer a task or a model from previous tasks to a new task? We just don't really know. Right? I think we need a lot more experiments, a lot more science going into that. So that brings me to a final challenge. Can we actually start building learners that never stop learning, that go from task to task to task? Some tasks can be very similar, some tasks can be very different, but it has to never stop learning. It has to learn across these tasks. And it also has to learn, these agents has to learn from each other. Right? If one learner learns a very good representation or a very good pipeline, some other learner should be able to reuse that pipeline or to reuse that feature representation. Right? And we can build a global memory where these systems can talk to each other and can share their information. And then if you have that, then you can let them explore by themselves. Let them use active learning to actually use what's there, use what we know, what everybody knows, and to build new models. And that will bring us to true automatic machine learning, where these models efficiently use any information that it had before to build new models for new problems. Thank you. All right. Questions?
You can queue behind the microphones around the central aisle if you have any questions.
Okay, so thank you very much for your inspiring talk. So my question is about tasks. So I know that by using meta learning or transfer learning, the agent can actually generalize the previously learned knowledges to unseen situations or tasks. But when you look at human beings, their behaviors might be driven by, curiosity or maybe just desires where there is no specific goals to achieve. So if we continue working on transfer learning or meta learning, do you really think that we can actually create truly intelligent agent, which can, spontaneously create some, behaviors or something like that?
Definitely. And I think that this notion of creativity is super important. Right? This also what defines us as humans and intelligent beings, is that we seek out more information. When we don't know something, we're curious about it, and we either start reading up, or we learn more, or we start experimenting and gathering more information. I think it would be very good if we can build algorithms that have this curiosity and learn actively. Great.
Maybe sometimes I think the acquired experience might be used for the future tasks or something, and then they don't know. Maybe the agent don't know how to use this experience to achieve some tasks, but maybe in the future they can do something. So maybe it's, as you said, maybe it's important to store some memories.
Yeah, exactly. It's like we have the internet. We should give machine learning agents like an internet where they can find tasks and models and things in an organized way that they can learn from that.
Thank you very much.
I have a quick question. So I was wondering, do you think in the distant future that there will just be one intelligent model that does well for all tasks, or do you think there will still be many dedicated models for a specific task?
Well, you can't really have one model for all tasks, but I think you can have a system or a meta learner that knows so much about the world that it can build a model efficiently.
So you don't think it will be one AI system that can learn it by itself and does well for many tasks at the same time?
Well, there's this thing called the no-free-lunch theorem, right? So you can learn good models for a task. You can meta-learn good models for a group of tasks, but one model that solves all tasks is kind of not possible because you don't have the necessary inductive bias to learn efficiently. Or maybe it's theoretically possible, it's not efficient to build one. It's much more efficient to learn how to learn models for certain types of tasks.
Okay, thank you.
Thank you.
Hi, my question is addressed more to previous speaker. Are there any techniques to overcome high performance variance? So for example, if we have a model that gives high variance from training to training, and what type of optimization will perform better? Will Bayesian optimization perform good under this setting of high variance performance?
Did you understand the question?
Can you repeat the question?
I'm sorry, can you repeat the question? I understood it's about high variance and Bayesian optimization, but that's about all that.
My question is if the performance has high variance, and we want to do hyperparameter optimization.
Yes, okay. So if you have a high variance black box that in repeated runs give you very different performance, then, well, you need, one approach that you can, for example, use there is, again, a multi-fidelity approach where you evaluate only once for kind of all configurations, but for the best configurations, you actually want to evaluate more and more. So the thing that you return, you actually want to be very sure about. So for example, in reinforcement learning, you want to do multiple trials because there is a lot of uncertainty, a lot of variance across runs. And so for the best configurations, you actually want to do a lot of runs, but you don't want to waste doing, for example, 100 runs for every configuration. So yeah, you can use a standard multi-fidelity approach for that.
So these AutoML models could be pretty complicated. So how do you make sure that the model actually learns something that makes sense?
You test it. you set up a testing environment where you test for what you want it to do.
Yeah, and of course you need a generic way of having lots of benchmarks. You don't want to overfit to one particular benchmark, but those are standard questions of experimental science, right?
How about problems like domain shift? Like your model is fit on data of a certain time period, but going forward in future, maybe things don't look like that way.
Yeah, this is called concept drift. So there's different ways of solving this. You have some algorithms that naturally adapt to that. Like most gradient-based algorithms, they do gradient descent until some point, and if the data changes, then the surface changes and it optimizes further. So those kind of adapt automatically. Other algorithms, you just have to retrain every time period. So it has to adapt to new kind of data.
Yeah, and you will overfit to the types of data sets that you see. If you see very different data sets going forward, then, well, you can have a component that looks at the data set and for these types of data sets uses different types of AutoML methods.
Okay, last question.
Actually, meta-learning is usually solving the problem classification and reinforcement learning. I'm looking for metadata for object detection task. Is there any open source like metadata, or is there any process that I can create metadata for object detection task?
I'm not aware.
Sorry?
Is there metadata for object detection? Are there lots of data sets for it where you can train on?
Well, OpenML has a lot of these, well, not things like ImageNet or something else, or
maybe it's a call to arms to the computer vision community to create such data sets.
Like
there might be some, I'm not sure.
Image classification, definitely. Object recognition, I'm not entirely sure. I'll look into it and get back to you.
All right, so this concludes the tutorial on AutoML, and let's thank the speakers again.